Good morning, ladies and gentlemen. Thanks to the introduction, Duncan. As you mentioned, I'm Head of Content at TCT Group, Daniel O'Connor, and I'm delighted to have these gentlemen join me on stage today. Each of our inductees was put forward by our Expert Advisory Board, and then they were nominated by the general public, which I think is a real belt and braces validation of their impact on the industry. Ahead of the announcements, the TCT editorial team and I, which is Laura Griffiths and Sam Davis, who's sitting over there, we got together and we did a podcast, and we talked about our favourite facts about each nominee for the TCT Hall of Fame. One of our inductees behind me coined the term three-dimensional printing, and the other brought the first ever metal 3D printing process to the United States. So what I'd like you to do, gentlemen, is just introduce yourselves by way of explaining that fact a little bit more, putting a little bit more flesh on the bones for that fact.
Sure. Well, good morning. I'm Greg Morris, and my background was, along with two other partners, my brother Wendell and a mutual friend, Bill Nowak, starting Morris Technologies back in 1994. We were a service provider all the way through our history. The short of it is that we started with stereolithography, got involved in other services and other additive technologies. But really, the game for us changed in '03 when we brought over to North America the first additive metal machine, which was an EOS DMLS 250, M250. So we brought that machine over. We thought we were going to be really smart and have a bunch of mold-making applications to make quick molds for injection molding and maybe make a few parts, and we were, of course, dead wrong. There was a lot more demand for direct parts than there were for mold inserts in North America at that time. So over the course of time, we continued to reinvest in the technology, getting more machines, better materials, and figuring out how to run these machines and create a bunch of different types of geometry, probably heavily aimed at the aerospace and the medical markets. But in the end, we started working with one of our customers in Cincinnati, right next door to us, GE Aviation, worked on something called the Fuel Nozzle, which many of you probably have heard that story ad nauseum at this point. But we worked on making the Fuel Nozzle for them, and eventually that led to GE's acquisition of our two companies, Morris Technologies and our sister company, Rapid Quality Manufacturing. And that happened in late November of 2012. So for the past 5 years, I worked for GE, and then just recently decided to take a break and spend a little bit more time with my family. So that's where I am today.
Thanks very much, Greg.
Sure.
Hi, my name is Ellie Sachs. Full name is Emmanuel, gone by Ellie since I can remember. I started in 3D printing in the 80s, so I was in the first guard. And I happened to see a beta site of a 3D Systems early stereolithography machine, and that's when I decided to jump in. And so together with colleagues at MIT, I worked on 3D printing for 12 or 13 years. A number of companies were spun off out of our work at MIT. I then switched for about 10 years to photovoltaics, solar cells, actually a field I had been in also before 3D printing. Worked in that and came back to 3D printing in the form of desktop metal about 3 years ago.
Our previous keynote from Dave Burns was on the thrills and chills for startups and getting started. In the early days of 3D printing, when you first invented it, there must have been some thrills, some chills. Can you just tell me about a time when perhaps things didn't go as well as you did hoped, and what you learned from that failure? We'll start with you, Ellie.
Sure. Well, nothing ever went wrong, of course. Never, hardly ever, or all the time. So I have a couple stories. Let me share one and then hear one from you, Greg. Our strategy at MIT in the early days of BinderJet, which, by the way, we called three-dimensional printing. Our first patent was called three-dimensional printing techniques, and that was the name of the project. Our strategy was to license by application, by field of use. And that was because we were exploring so many different applications in the beginning that we thought that was the best way to move forward. And it very well might have been. Who knows? You never know how the alternative would have worked out. But one of the licensees was for medical applications. So I think we were the first group in 3D printing to explore medical applications. A couple of my colleagues were very well versed in that field, including in tissue engineering. And so one of the licensees was for medical applications. And it was actually to a large, very large pharmaceutical company, the license. So we were really excited about that. And it was to their entrepreneurial arm. So their intent was to do a startup. So the idea that you have a startup backed by one of the large both pharmaceutical and medical device companies was really exciting. But as Dave Burns said earlier, choosing the right people is, well, he put that number 2 in reasons that companies, startups have problems. I would put it as number 1, 2, and 3. And it isn't just choosing the right people, but just people. And unfortunately, by the choice in this case of a CEO made by this licensee, that company struggled mightily. A remnant remained and came back to life, but it was an enormous potential that was not realized, and very, very early in the game.
And yourself, Greg, is there a time when things went wrong?
Yeah, gee, if I start twitching, it's going to bring back memories of all the things. Now, we had a ton of things that, some small, some big, some medium that went wrong, and some humorous, I guess. Didn't seem so funny at the time. I'll just give you 2 examples. One was, as I mentioned before, we started with stereolithography as the first rapid prototyping at the time technology. And we realized that we had a 250, so our build envelope was that 10-inch cube. And we realized as a business we needed bigger parts. And so at the time, we were, as a startup, we didn't actually do what Dave pointed out, going out for financing and getting seed capital that way. We actually did, we had one of the items, which was the family. So my parents very generously allowed us to borrow some money to start up. So we were on a very, very tight budget. So we couldn't afford at the time to go to 3D Systems and buy the SLA 500, which was the step up. That was going to give us the bigger build envelope. So to get over that, we decided, well, we'll get a machine that's an additive machine, but we'll get one that's a lot less cost. And that happened to be, for those of you who've heard of it, the LOM technology, laminated object manufacturing. And I think as a decision point to get into larger parts, it was good, but there were a lot of differences between LOM and SLA. So SLA is a polymer-based, laser-based process with a low-power laser, as many of you know, that's photo-curing the material. The LOM process took, in essence, butcher paper with a glue on one end, back side of it. So you put this big roll of paper onto the machine, and you have a build envelope, and the paper goes across the build envelope. And then it has a laser that comes down to cut the shape of that particular layer, and then cross-hatch to the little cubes the rest of the platform area. The platform drops, new paper comes across, a heated roller goes across and heats that paper and glues it to the layer below it, and the process repeats. So all that sounds pretty good, but paper, lasers, and heated rollers don't always mix and match. And there were a few times that we had some fires in the machine. One time in particular, it was like 3 in the morning. Back then, they had a little pager when the machine was raising its hand saying help. So I get up at 3 in the morning. I was the guy on call. I go into the office, and sure enough, that machine had done a number. It actually had not completely burned up, but it did a pretty good job, set off the fire alarms, and set off some of the systems. We had a third shift guy that was there already. He had taken one of those chemical extinguishers to put out the fire, and of course that left an incredible mess through the whole facility. So that was an ugly moment, but we still survived and got over it.
I think I've heard that even when they were working those machines, they still smelt like fire.
Yeah, they
Smelt like
did.
burning.
Yeah.
So quite often we'd have, it was Nottingham University, I think they had a security guard who would go around the premises, and he smelt burning, so we just shut the whole thing off. It was the middle of a 12-hour build or something like that.
Yep.
The 3D printing industry or the additive manufacturing industry has moved on from being purely about rapid prototyping. As the OEMs, they look to gain a foothold in what some call the $12 trillion manufacturing industry. You've both played a part in that process. Ellie, what was it that made you want to develop a 3D printer using an engineering grade material as opposed to, say, just fit and form?
Yep. So I had built things as a kid from as long as I could remember. And in college, I fell in love with manufacturing. I actually taught as a teaching assistant manufacturing class, and I taught machining, worked in a machine shop a couple summers. So as I mentioned, I saw a beta site of stereolithography, and I just instantly recognized the potential because I knew how hard it was to make mechanical prototypes and how long it took. I was also involved at that time as a research project at MIT in process control for making integrated circuits. So those are, of course, also built in layers, and that's inherent in that technology. So the correspondence was very clear between building mechanical parts in layers and building microelectronics parts. But having built stuff, I wanted to build in what I called real materials. You have to keep in mind that the photopolymers at that time were early acrylic based. They were dimensionally unstable, they were very brittle, so very limited material properties. So I set out to work in metals especially, and also in ceramics. And because I was thinking about manufacturing all the time, I set out to come up with a technology that could grow into manufacturing. So that was an express goal right from the beginning, was to come up with an idea that might have legs going forward, not just for prototypes, but for manufacturing. So I thought that would happen right around the corner, of course. It's 2.5, 3 decades later, but it is happening now, and that's super exciting.
And for you, Greg, as a long-term user of the technology, when did you realize that actually, these parts, these forms, we could make them for production purposes or for manufacturing purposes?
Yeah, I can actually, we really had our specialty that we carved out in the metals. And again, as I said, that happened initially, it started in 03. But, those early alloys that we worked with, they were direct metal, which was a bronze-based alloy. It was the direct steel and direct steel H20. And they were good. And in fact, I still to this day remember I was first introduced to that technology at Procter & Gamble, one of the customers of ours. I was over there for a sales meeting and met with this guy who was leading that department, and he said, "Oh, do you have a second?" I'm like, "Sure." And he comes out with these mold inserts, and he showed me them. They're made out of direct metal, so the bronze-based alloy, and it was better detail resolution than anything I had seen up to that point in the industry. So that's why we invested. We ultimately researched, invested, and brought, as I said, the technology over. But what we quickly found was that the bronze-based alloy for parts, for direct parts, and the steel and the H20 steel, direct steel H20, they were good, but the problems they had were the mechanical properties weren't fantastic. We had corrosion issues with the steels, low-carbon steels. We had a lot of stress cracking issues in the DMLS machines because we were using lasers, at that time a CO2 laser, et cetera. So I really pinpoint the huge shift in what happened to 2005. So in '05, as I mentioned before, GE was one of our primary customers, and we were working with them pretty closely. Two individuals in particular, one in their test facilities engineering, one in the combustion group. And they kept prodding us to come up with a better material than the direct metal and the H20 and the direct steel for the reasons I outlined. So we in turn kept prodding EOS and saying, hey, we need something better. Do you have a nickel-based alloy, an Inconel, or something of that nature? They had been working on an alloy called cobalt chromium, and that ultimately was through a variety of different negotiations and a little bit of arm twisting perhaps, we became the pilot customer in North America. It required a new machine that had the fiber laser versus the CO2 laser. So we bought the 270, we put in the cobalt chrome material, and it was not overnight. It probably was about a year, 2 years in of lots of testing and lots of producing a part, sending it to the GEs of the world and getting feedback about, well, it didn't turn back into powder and it didn't corrode. And what we found actually over time is that our low cycle fatigue and our high cycle fatigue and our ultimate tensile strengths and all these mechanical properties that are so critical to high-end applications like aerospace or even medical implants, the material looked very much like it was going to be something that would be highly useful. So, that was just a pivotal moment in our company and probably overall for the industry is to see the maturation of the technologies go from a cobalt chrome, highly useful material, and then of course now we see many, many different materials, nickel-based and stainless steels and all kinds of stuff. But that was really the beginning of the belief that this technology could not just act as a prototyping technology, but we were crossing over the line into it's a production capable technology. And of course, it's taken years still to get the speeds up, the costs down, the quality systems there. But we are on the precipice, if not even over that at this point for some specific products. But for us, I'd say it was '05 really was the beginning, and over the corresponding 2 years, the feedback that kept coming back really gave us the green light that this was going to be something we hoped pretty revolutionary.
And on that topic of materials, Ellie, at the moment with desktop metal, would you say that the metal injection molding industry has really changed the game for you and that technology?
I'm sorry, could you repeat?
Would you suggest that the metal injection molding technology and the powders that we're seeing now and the use of it has really affected desktop metals
Yes,
growth?
very much so. In fact, back during those 12, 13 years at MIT, we started to work with the fine powders from the metal injection molding industry. And we made some tiny little parts that we were very proud of, but there were several problems at that time. And one was that the MIM metal injection molding industry was really small and not of the highest reputation. So people would, if you were thinking about having a part made by MIM, people would invariably interpret that as an act of desperation. And that's probably true at that time. So it was tiny industry, not good reputation. Powders were very, very expensive. So when I went out to try and convince people that this was a good path, that was one of the problems that I encountered. So that's been a huge change, driven in part by applications in electronics, consumer electronics, but lots of other fields as well. So people no longer have that reaction. So that's been a very important thing. But another important aspect has been the progress made in inkjet printing. So back when we were doing a down select between, in the 80s, between a couple of, about a dozen ideas we cooked up, one of the arguments that I encountered, I guess this is after we made the down select, is people would say, well, look at the desktop publishing, the printer business. Inkjet's losing, they would say. Laser's winning. You've picked the wrong horse. And my response, at least my response in my own head, was I had visited lots of inkjet printhead companies. Being a professor, they tend to be just a little bit more open, so they were sharing with me their visions and sort of what was in the back room, and I could get a sense of what was coming. So basically, I was placing a bet that while inkjet was probably losing at this moment, that was not necessarily what was going to happen in the long run. So, so now there are quite a number of suppliers of very impressive inkjet technology. So that's helped as well.
I'd just like to move on to design for additive manufacturing. It now has its own acronym. We see DFAM written down a lot these days, which shows that we've made some progress. But in the early days, Greg, when people were coming to you as a service provider, what was the design for additive manufacturing capabilities like? How many times did you have to go back and feed yourself, Ellie? When did it become apparent that we needed to change the way we think about design?
Yeah, I would call it almost non-existent back in that 2005, if you will, timeframe for quite a while. I mean, I think we were learning as a company that had the technologies internally. So you can only imagine how difficult it would be for somebody in an OEM that we would approach and say, hey, this is a great technology. You ought to think about creating better designs or combining components into one part. So we had to do a lot of evangelizing out there and trying to go back to the basics with customers about why they should even consider additive. I mean, design was the number one item you had to get over as a hurdle. Because if you just tried to make typically the part that they had designed for traditional manufacturing technologies, it probably wasn't going to be a good part to make an additive. I mean, we had our share of parts that we would say, all right, they were insistent upon having it grown additively, and we'd try it, and of course, we'd have a lot of problems on the build because we had thick sections and areas on the platform that would pull up and all kinds of issues. So it really took a lot of arm twisting sometimes and convincing and just time to get people to change their point of reference for how they should be treating design and additive. And I think now, even today, I would tell you that very few OEMs and very few companies out there have a solid, deep understanding of designing for additive. And when I say that, I'm not necessarily talking about the actual design and structure of it, but the design and the mechanical properties combined, and what does that all mean? Back to, I'll use GE as an example. On their catalyst engine, which used to be called the advanced turboprop, they went from 855 traditionally manufactured components down to 12 additive. So they combined 855 traditional pieces to make 12 grown parts. So that doesn't just happen overnight. That happened because there was enough time for the GE designers and engineers to work with the technology, started with the fuel nozzle and graduated up into something bigger and better. And goodness knows, I suspect they have many, many more parts now that are going to be working their way into the engines of the future, where they've really leveraged that design element. But it wasn't easy. It isn't easy. And although I think we're starting to see the momentum build, we're still probably a long way from companies fully grasping and having that. The other thing I'd say that prevents some of that happening is that to do 855 to 12, you have to think on a system level, not a part level. So that's super important because a lot of companies are structurally not set up to be able to have a system level organization. They're very siloed in their organization. So in automotive, you might have the drivetrain people, and the drivetrain people focus on drivetrain. They don't necessarily concern themselves with other parts of the car. And you really need to have that full view in order to be most efficiently designing for additive. Otherwise, you won't reach the full potential.
And what about yourself, Ellie? What was it like when your earliest printers, what was it like with the early designers that were using your technology?
I'm sorry, what's it like?
What was it like with the earliest of your printers, and what was it like when the designers were manufacturing for your technology?
Yeah. So, if you think about in the early days, late '80s through the '90s, making an argument to take advantage of the geometric complexity, especially the ability to do internal geometry, you really had to find applications where you could argue that you could do it in production. At least that's the route that we took. So on the one hand, we were saying that our inkjet technology could, in the future, do high rate production, but in fact, we were not doing that at that time yet. So we had to look for applications which were very high value and made in sufficiently small numbers, so similar to I think the aerospace area. So, for example, we did some work in orthopedic castings, specifically knee castings on the bony ingrowth surfaces. And that work was actually done through casting. So our first application, in fact, for 3D printing, or what we call now called binder jet, was to print ceramic molds into which you poured metal to make a casting. And so that's the route that we were following. So we printed molds that would be extremely difficult to make by other means. And we were working with J&J, Johnson & Johnson Orthopedic, and they cast these very intricate bony ingrowth surfaces, did rabbit studies. Results were really good. Unfortunately, that, for a variety of reasons, that did not get commercialized on that path. But you can see examples of that in direct metal now out in the hall for hip balls, for example. So you had to look for these very specific applications in order to make that argument. We also looked at using in binder jet, you can print material, not just a polymer binder, but also material through the inkjet nozzles. So we looked at making what are called gradient index lenses, where the lens refracts light not because of the curvature of the surface of the lens. It's a flat slab, but it refracts light because the index is different from one place to another. So we actually made some little GRIN, so-called gradient index lenses, as proof of concept. But at that point, the economics just wasn't there. But you very much or at least our perception was that you had to be very, very targeted. In that project, I worked with other colleagues at MIT who were experts in CAD. So we developed some early CAD add-ons in order to support the local composition control. So it was very attractive, right? But very hard to really get a foothold.
When you and I talked on the phone for the TCT podcast, you mentioned that there was a sort of happy coincidence in when you were making these ceramic molds that the material happened to be porous, and that made it very sensible to use for that application. Can you just elaborate a little more on that?
Sure. Yes. Well, so I had before getting started on 3D printing, I had visited every factory that I could, basically, that I had time to and that let me in. So I had visited several investment casting houses and automotive engine block casting. So I had in the back of my mind that and I remembered because it was a surprise to me that those molds, those ceramic molds that you pour molten metal into, are porous. And so you might say, well, why doesn't the liquid metal just pour through? And the answer is because it doesn't wet the ceramic. So it's not like a sponge, but rather it's as if that mold were made of Teflon powder and you were pouring water in. It would just stay in there and not pour out. So I had that in the back of my mind, and And then when we looked at our list of ideas and we saw this idea of inkjet print into a powder bed, I realized that it was going to be another challenge to consolidate the part, that is, densify the part. We were going to make out of the machine a porous part. So if we wanted direct metal, we would have to either infiltrate or sinter, which I was pretty sure we could do, but I was looking for an application that didn't require that. And so here was a natural marriage to print ceramic, have it come out of the machine as porous, and that's exactly what you wanted for metal casting. So that was actually, it was that recognition that led me to choose inkjet printing into powder from the list of crazy ideas that we had. So turned out to be a fortuitous marriage.
And that's an application that most businesses or manufacturing companies in the UK could use. What do you think, and I'll ask you this question, Greg, what do you think the current barriers for small to medium enterprises to manufacture with additive? Is it the materials, the technology itself, the ancillary equipment, all of the above, or what do you think?
Yeah, well, the easy answer is it's all the above, but I think I'd actually go even beyond just small companies and job shops, and I would expand that out to almost any company. As there's still a lot of barriers. Things are clearly moving in the right direction, and progress gets made every month and every year, and I think some of these obstacles are overcome. But look, I mean, the journey's difficult to get into production with these things. Now, if you're, so you have to kind of look and say, are we talking about a prototyping type application, which is a little lower bar, if you will, for complexity, or the production opportunities where I think a lot of people want to get to, and for obvious reasons, the volumes are higher, the dollars are higher. But for the production technologies, I mean, you look at the machines today. I mean, they're very expensive. So for a small shop, I can't. It was expensive when we were buying machines. I mean, we'd be spending hundreds of thousands of dollars for every machine that we would buy that would have that 10 by 10 envelope basically in the metals. Now we've got machines that are much bigger, and these are, obviously, as many know, over $1 million. And some of these machines coming out are multi-million-dollar machines, at least on the laser-based and on the EBM-based, okay? Different story, clearly, for binder jet and for some of the other modalities. But so that's a challenge. I think, the technology itself has come a long way. But look, let's be honest, there's still issues on the technology side with the machines as well. And again, I'm focused on laser and EBM. I'm sure there are issues on all the other modalities as well. But there's a learning curve, and are they ready for that? Like Dave was saying, 24 hours, 365 days a year type operation. And I think some and certain applications can do that. And clearly, I look at GE and what they're doing for their fuel nozzle production and some other parts, and it seems like they've got that kind of a production going. And so I'd say it's possible, but that didn't happen without a lot of people, a lot of expertise, and frankly, a lot of modification and things that the GE world brought to those machines and those processes. So look, there's a lot of complexity to get there. The certifications, depending on what industry you're going to be in, if you're selling parts to, again, the aviation, aerospace, or medical markets, you have to have the right certifications, not just talking getting your ISO AS9100 or 1345 plaque. It goes much, much deeper. And more than likely, if you're working with an OEM like a GE, you're probably having to conform to their quality systems and having to prove what your systems are under control, et cetera, et cetera. So, yeah, a lot of barriers, but also, as everybody at this conference, and as Dave was just saying before, and I think all of us would agree, the potential is quite large.
And for you, Ellie, what do you think the current barriers are?
Yeah, I think when you're moving from prototypes to production, reliability becomes number one concern very quickly. So I think that's still somewhat of an issue. Obviously, less than it used to be. I think at the core, it's a question of rate and cost. that constitute the primary barriers. So if you look at it was interesting in the 80s. It seemed that CNC machining, computer numerically controlled machining, had taken a pause in development. And it had advanced. It was originally developed in the 50s, and it had advanced rapidly, but then it seemed to be taking a pause. And so I think some of us who were early in the field, at least I was a little bit fooled by that, I have to admit. And maybe it was just a natural pause and that progress would have resumed. Maybe that progress was a little bit kicked by 3D printing as a competitive threat. Who knows? But CNC machining has come a long way. It's quite amazing, right? So at least in the job shop context, that's what you're competing with. So the costs have come way down. Tooling life has gone way up. Precision has gone up. So I think that the cost and throughput are really substantial barriers, and I think we see progress on that. But that's my thought about what the primary
Yeah,
issue is.
if I kind of jump on that real quick, I totally agree with you. I think cost is a huge problem because it really limits the number of parts that you can consider to be putting into an additive machine. And in the end, as much as everybody loves additive technologies for the sexiness of it, it will probably come down in most OEMs to the cost of the component before anything else. But that being said, I think cost can be achieved in a lot of ways, and I'm sure you would agree with this, that you can achieve that cost target by brilliant design. And if you can do that combination of taking multiple parts down to one, that's a huge cost savings. And I really haven't seen any presentation or any published numbers that would really go deep into that cost savings on the supply chain, but it has got to be huge because you have less inventory in the supply chain, you have a lot less suppliers, you have a lot less engineers and designers up front, you have less assembly time, and on and on. So if you take those, whether it's 10 parts or 300 or whatever, down to one part, that's a huge cost savings throughout the supply chain, not just that direct part. And I think that's where today additive plays very strongly, unless you have some material combination that gets you something that you can't easily do in the traditional manufacturing. But to be clear, from my perspective, you talked about a 12 trillion total global manufacturing output number before, and depending on how you come up with that number, 12, 15, 17, doesn't matter. It's a huge number. And today, our little industry is something like 0.03% of that number. So if our little industry could just capture 0.5%, you're talking tens of billions of dollars, probably somewhere in that $80 to $100 billion in 5 to 10 years. And I think that's achievable by these specialized applications where you can combine parts, and that'll get some breathing room for some of the technologies like a desktop metal, admittedly, which that's a fantastic technology that can whip things out very quickly and has much higher speeds. And I think we'll see those technologies mature as we will the laser and the electron beam and all additive modalities to a point where they get closer to that CNC cost point. May not equal it, but at least I think that circle of applications grows over time.
Yeah, I totally agree. The point about huge opportunities for growth is absolutely correct, and I think all of this plays out in a virtuous cycle.
Yep.
So you make an advance in feature size or in production rate, and now that enables a new set of applications, and then that advance combined with this advance enables another set and another set and another set. So I think a lot of exciting things will happen over the next 5 or 10 years.
Do you think there's any kind of like cultural issues in terms of cultural business issues when it comes to additive? So, for instance, people who see it as this, novel technology that nobody cares about, and they've used it once before, and they won't go back to it now because it was building trinkets and Yoda heads. Do you think there's any that we've got to go any way to change that? I'll throw that to you.
I think that's changing. I mean, I think that could have been the case, but look, you've got too many convincing case studies out there at this point. Whether you're making shoes out of your carbon, carbon machine, or you're making fuel nozzles or LPT blades or whatever you're doing, these things are making it into the real world. So I think I have not heard people, executives or engineering departments, discounting additive at this point. I think it has made it to the level of people understand it can be very disruptive. I think the question is more, where is it going to be disruptive, and is it disruptive in my products? For folks like myself and a lot of others here, I mean, you could make the argument, well, sure, you're making anything, additive's going to have a big play somehow, some way. Will it make a play on the production side of things? Yes, sometimes that'll take longer, just due to certification, due to qualifications, whatever the case. But I think that at least my perception is, by and large, people don't look at it as a trinket type technology anymore. I think they realize that, in particular on the industrial systems and the industrial materials, that it's real and it's showing up in real life products, and not only real life products, but real life products that have high liabilities associated with them, such as aircraft engines and medical implants and other things that could be really ugly if there was a problem or a recall. So because of that, and knock on wood, I don't see any wood right here,
No, I don't think there's any
knock on
wood
my
here.
head, right? We won't have a major problem that surfaces. But even then, I think we've crested over to where it's been legitimized, and I think it's now back to that, how big a circle of applications do we get to? And that's a cost question, it's a maturity question for every company. But the culture of thinking of additive, to me, has shifted, and if it hasn't, shame on the company that hasn't gotten to that point yet.
Would you agree with that, Ellie? Has the culture shifted away? Has the culture of additive manufacturing shifted towards where we want it to be, do you think?
Yes, I think I agree with everything Greg said on that topic. I'll just add from the educational perspective, it's shifted enormously. As someone who has an organic love for turning dials on a milling machine or a lathe, I'm actually a little bit worried about just how far it's shifted, because a lot of young people think of, when they think about manufacturing, they actually think first and sometimes only about 3D printing. But the positive side of this, and I'm not just talking about in grade schools, which is happening. I'm talking about, for example, in our current version of the manufacturing class in mechanical engineering at MIT. There's a shop component with, fortunately, still a healthy dose of machining and injection molding and other things, but rows and rows of 3D printers as well. So these folks are just going to go out expecting this to be part of how they do things, and so as long as it's kept in the right balance, I think it's great.
I think that's a great point, and it's something that is not often talked about. I could not agree with you more. That if additive is your only tool in the toolbox, you're in trouble.
Yeah.
And as much as we promote additive,
right.
We absolutely, it's in additive's best interest to make sure it's used in the appropriate way, which means more often not, especially if you're in metals, you better have CNC machines or even manual machines, and you better be using traditional technologies, including castings and forgings and fabrications.
Right.
I mean, those aren't going to go away, not in our lifetimes, and maybe not in any foreseeable future. But it is a problem, because everyone likes the sexy technology
Right.
that come out, and
And there's also, from the educator's point of view, not so much at the college level, but at the younger level, at least in the U.S., shop class went out of style, and that was partly for safety concerns, right? And so, at least this is my perception. And so, additive offers a way to bring in manufacturing with much reduced safety concerns. So it's a very natural fit. So one of the things that always attracted me about manufacturing was that there's a very high barrier to entry for a new technology, because you have to, invariably, you're competing against other ways to do it, some of which have been around literally for thousands of years. Metal casting, for example, about 4,000 years. So there's a very high barrier to entry, but once you're in for a very long time. And so I think that will be true of 3D printing as a field, but in parallel, it will still be true of castings and forgings and stampings and the like.
Yep.
On that point about the future and about the youngsters using the technology today, there's a great deal of talks, particularly at shows like this, surrounding factories of the future, smart manufacturing, Industry 4.0. What goes hand in hand with that, certainly in what the mainstream media, is a worry about jobs. If, let's say, the factories do become smart, a part is designed generatively, printed and post-processed automatically, what do you think is the jobs of the future of manufacturing are going to look like? I'll let you go first, Greg.
Actually, Greg, could you go first? I want to take it in a slightly different direction.
Okay.
Sure. Yeah. I actually don't get terribly worried about. I mean, I understand what you're asking, which is you've automated things and thus you've taken away somebody's job that was maybe more manually doing something. So, look, I don't think that's going to happen. There's people a lot smarter than me, and people have done more studies on this that could probably give you a lot of facts and figures. Mine's just an intuitive feel that I don't see it happening. I haven't seen it happening. I'll use GE as an example. They have this facility in Cincinnati. They have multiple facilities around the world, but the one I'm actually familiar with the most is the Cincinnati facility. And for every machine, every additive machine that they've put on the floor, it seems like there's a ton more people that are surrounding it. So, you got designers, you got quality people, you got machinists, you have purchasing and sourcing that's helping with it. I mean, you have a whole organization. So I've actually seen the employment go skyrocketing over there. As they keep adding machines. And you've got technicians and you've got people that are the engineers that are helping to, figure out things on the machine. So I'd say that's one comment I'd make. And one last thing before before you want to jump in, is throughout history, you just cannot stop innovation. And it's a fool's errand to try. And why should you? Because I think it has been proven time and again that innovation will take things in ways no one can predict today, and I think that's going to be true for additive. So I think it's really a bad argument, maybe, or it's almost more of a politically convenient discussion to say you're going to take away jobs doing this. I would argue it's the reverse of that, and I would also point to, again, I haven't done the studies, but I would point to probably, if I thought about it long enough, hundreds of examples of where there was innovation, and innovation actually generated way more jobs than they ended up taking away. Even though there was a microcosm of jobs, or micro area of jobs taken away, there were a lot more ultimately in the broader context that were created. And I think that's the case. So I actually look at additive as being very, very positive. I'll speak for the U.S. A lot of parents don't think of telling their kids to go into manufacturing when they're in school. And I love the fact that additive is a sexy technology that actually starts to change that paradigm. And maybe we'll see parents say, hey, have you ever thought about getting involved in additive or getting involved in 3D printing, which is manufacturing in a different terminology. So sorry, I went a little longer.
No, that was great. So I'm often, not often, but I'm occasionally asked, how do you feel about working in 3D printing given that it's going to take jobs away? And I find that if they had asked, how do you feel about working in advanced manufacturing or manufacturing, where manufacturing jobs, at least in some places, are diminishing, that question I would understand. Why is focused on additive? I never understand. I try to explain to them that this is part of manufacturing, and it's no more and no less of an issue for 3D printing additive than it is for any other aspect of manufacturing. So that's just one point. I'm personally not quite as sanguine about the impact on society of advances in manufacturing and or just in general about the question of what people are going to do 50 years from now. I probably spend a few too many hours worrying about that, especially since there's nothing I can do about it. But what I do think needs to change, and so I split my time between Desktop Metal and MIT, and at MIT I'm engaged in with others in pushing a boulder uphill, truly Sisyphean challenge of trying to reinvent how to teach engineering. And I think that in general we have to reinvent education, because education is for the most part not about people learning how to think, which is what it needs to be. Because if you have to change careers, then you need a whole different skill set about how to think than you do if you were really being trained, which is what our education was developed 100 years ago to do. Trained for a job that you were going to do for the rest of your life. So to me, that's the change that needs to happen to accommodate these other changes.
Yeah, we're not going to have people running around smashing up machines because they're worried about jobs. Hopefully, like they did in the when the sewing machine first hit the Northwest. Hopefully, it will be a bit different than that.
My grown sons do accuse me in some areas of being a Luddite.
Okay.
So I don't know.
No, maybe. I was at IMTS a couple of weeks back, and I had this feeling that I was in a couple of press conferences, and I thought, we're still saying the same things that we were saying 5 years ago when I started in this industry. But then it was actually a visit to the GE stand, the GE Additive stand, and I spoke to a colleague of yours, Greg at GE Aviation, and he started to tell me that 5 years ago there was a handful of developments that were for additive manufacturing, particularly for the catalyst engine, and now there's hundreds in GE Aviation, and it's only been in 4 short years. Do you think that we're about to see an explosion of all of these applications? Is the next leap for Fuel Nozzle and the next thing's all coming in the next 12 to 18 months, do you think? Or
Well, that had to be a salesperson you talked to. Look, I think, and I'm not privy to where GE Aviation in particular is today on how many different parts they have in the works, but I know enough to know that they have they are doing some phenomenal things. There is absolutely no question about it. It usually takes a good couple years before anybody gets permission to publicly talk about what they're doing. That's GE and other companies. A lot of that's usually kept under wraps until it gets to a certain point of maturity within the organization. So I do believe there probably are many parts that are going to make their way eventually into future engines. But you have to keep in mind that for a GE, their engines, their primary set of engines are the larger engines. They're not the catalyst size engines. So that dictates you'll need bigger parts and typically and that kind of thing. But look, overall, my opinion is I think that in the next 5 to 10 years, we will see a substantial number of applications in polymers and metals, ceramics, and a whole bunch of different materials and modalities starting to make their way to conferences where people start talking about them more. It's just, it's on its way. There's a lot of things going on. Ellie, I'm sure can back that up with regard to their modality, which is a great modality for applications that may not have those, say, high cycle fatigue or low cycle fatigue. It's they're going to have huge penetration in binder jet in a lot of different areas, and there's going to be a lot of penetration in laser based and EB based and other applications and repair technologies. We haven't even touched on. It's another huge one for directed energy deposition. Radiated materials will open up whole new realms of things. So I think we're getting to that tipping point. I think there's enough, still a long way to go, but enough engineers and designers that are getting how that design for additive has to happen. A ton of companies out there offering the services and the capability. A lot of people more mature in their thinking about the processes and the quality systems. So I think it's not 2 years. I think it's probably, my guess is it's a little longer horizon, but I think that wave of stuff is coming soon.
And what about yourself, Ellie, from the desktop metal perspective? What kind of tech applications are you seeing come in, and what do you expect for the next 5 years?
Yeah, well, so may I speak a little bit more broadly to, so you often hear the word revolutionary associated with this field. And I think that has to be weighed against the kind of thing that I mentioned earlier, that the barriers to entry in manufacturing are very high, but once you're in for potentially a very long time. And so the word revolution is probably just not inappropriate in the lexicon. It's probably more like evolution, and I think of 3D printing as punctuated evolution. So evolution proceeds slowly, but apparently there have been times when it proceeds very rapidly. But even when that's proceeding very rapidly, if you're living through it, it doesn't necessarily look very rapid, right? And so I think that's part of where the mismatch comes. So you can look back, as you said, and say, I've heard sort of similar things for a number of years now. What's going on? Why isn't it coming to fruition? But if you could go forward 50 years, which in manufacturing is nothing, actually, and look back, you would look back at these, let's say these 20 years that we're in the middle of now, as one of those punctuated evolution stages. So it would look very rapid indeed in perspective.
We have a couple of minutes remaining, and we've probably got time for a couple of questions from the floor, so I'd like to open up to the floor. We do have a microphone. Magda has got a microphone there, so if you have a question for any of the two gentlemen, please put your hand up. Any questions? You're not going to get this opportunity again. Okay, well, thanks very much for your time today, gentlemen. It's been really interesting. Thanks for the talk. Congratulations on being nominated into the TCT Hall of Fame. And I will see you this evening at the TCT Awards. Thanks very much, Greg.
Thank you. Thank you so much.
Thank you.
Thank you.
Cheers. Thanks, everybody, for coming. Thanks.